towards accountability-driven development for machine learning systems. This research is supported by the RAINS project funded by EPSRC. Please allow me to take the 2 minutes out of the 10 minutes to thank the organizer for accepting our paper first. And thanks also to Dr. Pan and other authors for their help in writing this paper. And we have received some peer reviews. Those are all valuable for our future works, and thank them. In our paper, we briefly introduce a framework called accountability-driven development for machine learning systems. It illustrates how to consider accountability of ML systems from beginning of the development and transfer accountability requirement into test scenarios. This is the high-level stage of ML system development. What's the accountability of ML systems? This is one of the definitions we use in one of a previous paper from our research members. It's the ability to inspect, review, or otherwise integrate an ML system with the goal of making process associated with each of its life cycle stage transparent, demonstrating compliance with hard laws and soft laws, aiding investigations in the course of failure of enormous decisions and supporting the identification of responsible parties. This is a typical machine learning workflow. So we can see the implementation stage is actually for non-technical development members as a black box. So in the development team, decision makers care about the purpose of the application. Stakeholders are concerned with the business value of the potential application. And domain experts explain what the data means. Data scientists and ML engineers focus on technical perspective, including data processing, model training, and evaluating. And this division of labor may cause ambiguity for accountability of ML systems. It's difficult to identify who will take the responsibility when an error occurs. Also, there's a technical barrier that keeps non-technical team members out of the development, cause a waste of potential contribution for accountability from them, as they may have better understanding of law, ethical metrics, etc. This is our framework, the accountability-driven development workflow. See, we can see that we can consider both the technical and task analysis and the accountability requirement analysis together to decide the testing scenarios. We will discuss later on in next slides. Okay, but similar to the behavior-driven development BDD, ADD is a task-driven development approach. Use natural language to describe text scenarios. Engage non-technical collaborators drawn deeply into the development. Consider accountability at the beginning of the development by combining technical and accountability requirements together to decide test scenarios. The first test is similar as the BDD. It must fail because there's non-model existing, and then until the ML engineer, they conduct the implementation stage to construct a model. And The model will go through the tests again and again until the model passes all the tests. During the testing, we will ask the system generate information about its performance, its explainability, and transparency to fulfill the accountability requirements. And those information will be documented. What's technical and accountability requirements? Technical requirements refers to performance characteristics is normally come with the potential user or the initial idea from the development team. That include performance requirements, safety requirements, hardware architecture requirements, etc. So accountability requirements, it prefers the information about systems performance, fairness, transparency, and explainability. Have them been generated? Have them been properly documented? For example, the information about hardware architecture requirements, we can design a test to ask the model to give what GPU or CPU it's running on. For documentation, we can design a test to ask model over a document that mark down all the information. So extend model card is one of the solutions. This is one of the JSON structure I will agree for collect the information. It's quite similar as the model card they proposed. So we can mark down some manual capture information, for example, the name of the model, overview of the model, something like that. Okay, how to design user story scenarios. So the first, we use natural language and consider both technical and accountability requirements, and consider edge case use cases. For example, what's the edge case in an automatic decision-making system for mortgage applications, and then when there's an edge user case and that an applicant with no features go into the system and the error message wrong input given cannot create proper output should be given rather than the normal output as mortgage application is approved or mortgage application is declined. An example of testing scenario and a syntax. This example is based on an automatic decision-making system for mortgage application. So the title is producing non-discriminatory outputs. So as a bank, I want a system that produces fair outputs for different applicants regardless of their ethnicity, so that the system is not racially biased. So the scenario one is a system should produce fair outputs for applicants from different ethnic groups. So given the mortgage application approved for applicant A, when another applicant B with the same features but different ethnicity applies for the same mortgage amount, then the mortgage application should be approved for applicant B and cost-wise. Okay, discussion and future works. ADD is one of the solutions to create and capture accountability information in implementation stage of ML system development regarding system performance, explainability, and fairness and transparency. The use of natural language allow all team members contribute their domain knowledge to improving systems accountability. So the next step, we are going to improve this framework by making a deeper study in the requirement and scenario design section. and extend this paper by giving more detail on what to capture. Honestly, in this paper, I haven't give a full list and what to capture, what information need to be captured, and how to capture. We just give a framework. We haven't give a solid example and to explain how to capture. But we give a approach just like a model card and integrate model card into our framework to capture the information, and give 2 solid examples on different domains. Furthermore, we are going to extend ADD to whole ML system life cycle. Finally, we are considering developing a computer-like tool, and that is specifically for ML system development. Thanks. Okay, I will leave some maybe about 5 minutes for questions and comments. Thanks for your attention. Okay.
Thank you very much for a wonderful presentation, Chiu. Do we have any questions? If we do, just raise your hand and we will. All right, I can see when we've got one from Nirmali already. That was fast.
Thanks, guys. Just a quick question, Wei Pang. You mentioned that there's the need to capture this information. I just wondered, like, what is the manual demand on collecting all this natural language text? Do you see a challenge there, or what are your thoughts on that?
Could you say again, please?
So you mentioned throughout the workflow, there's like information to be collected and so on. And I think what you're suggesting is maybe that also provides useful explanations. I guess my question is what is your thoughts in terms of the manual demand on collecting that information and sort of curating it into explanations and so on?
Actually, in our paper, we have another example for the explanation information capture. That is, for example, how to say, it's quite difficult to list a full list and what's the explanation information to capture in one case study. But we are trying to do in the future. But in our paper, we give one example to capture the explanation. For example, in a mortgage application, automatic decision-making system. So we ask the model to pass the test by asking, give an explanation about the features of the applicants and how important and which one is most important to affect the outputs.
Thank you.
You're welcome.
Okay, and we've got another hand raised from Wei Pang.
Yeah, just a response to Nirmali's about the manual demand. Actually, there is not possible to generate a large amount of interpretations or explanations from the model, right? And what we do is, to hold the algorithm or the developer accountable, we need to require the developer to actually to think about it, or to even they cannot produce those information. We need them to think about what will be the approach to produce them, and this is one way of holding them accountable. And if something happens, we can trace back and say, okay, you have think about this method. Now we are going to use this method and see what happens. So this is one way to deal with the large amount of manual work. So
okay. I see. Thank you very much.
I've got maybe one last question before we move on to the next talk. One of the really exciting things I find about this, Chiu Pang, is the idea that you can use cases generated in natural language as a means to assess your system, which enables you to bring in groups of stakeholders that traditionally wouldn't be able to evaluate explanation or your AI system. And we see this a lot in likes of user-centered design research or HCI research. have you considered about where they may play a role in these user story or use case design scenarios that you might look to integrate with ADD?
No, we haven't. Yeah, that's our future work, and honestly, and we just briefly introduce a core idea how to do with it, and then the next step we are going to do what you're asking for. Yeah.
All right. Perfect.
Okay. Okay.
Thank you very much.
Actually, we are doing something already. Like, for example, I have wrote a GUI to create a document automatically and then collect the information when the model pass the testing scenarios. But it's not enough to put this paper to a conference, and we still need to do further to make two solid examples to achieve the better version of this paper. Yeah.
No, that completely makes sense. No,
Right.
It's certainly very interesting preliminary work. So very, very well done on what's done so far.
Thank you, Cal. Thank you.
Okay. I guess with that, if you could stop sharing your screen, we'll move on to paper 2 for this session.
Yeah.
And so in paper 2, I believe we have a bit of a mirror of the authors list for this particular paper as well. So paper 2 is on evidence capture for accountable AI systems. And this one is by Wei-Pang, Milan Markovic, Iman Naja, Chiu Fung, and Peter Edwards. So without much further ado, Wei-Pang, if you're ready to present.
I'm sorting out the firewall issues. I have to quit my it's a Mac issue. I'm trying to, so did you see my, sorry.
Yes. Yeah, I can see your screen. I can see.
Okay, that's fine. Oh, yeah, okay, that's fine. Thank you very much. And I'm going to, right. Okay, so I'm going to talk about part of the RINS project. Is the same project, as in the previous talk. And I'm Wei-Pang. I'm the associate professor from Heriot University, and I'm also co-I of this RINS project, realizing accountable AI. And RINS is funded by EPSRC, involve lots of universities: Aberdeen, Heriot, Cambridge, and Oxford. And so I'm leading one of the work package about information capture for accountable AI. That is, how we can capture, useful information to realize accountable AI. So I thank the founders, the rest of the RINS team, and also the partners and stakeholders, and also 2 of the students who work with me at Heriot, and they help this research, and also the partners. We have a lot of meetings with the partners to help us better understand the real world situation. So I've talked about why we are going to do this research, and then I will talk about the scopes of AI accountability, and then we will try to answer 2 questions: what do we need to capture, and how we need to capture the information for accountable AI. Okay, so this is part of the RINS project. So in the RINS, we trying to work with a number of universities and people from the law, from social science, and the partners. We're trying to understand, what do they mean by accountability AI, and what do they want? What is useful? And specifically for our piece of work, and the work package is about the information capture. So once we capture the information, we will actually inform the core RINS component with we call the accountability reasoning, and this is realized by the RINS ontology. And the accountability reasoning framework will actually manage the central the reasoning and the managing deal with the queries of the accountability issues of all across the AI lifetime. And so it's very important for us to have the effective means to capture the information for accountable AI. I would like to share, this is not a technical paper, it's more like a lesson that we have learned. We want to share with the community. And also we hope people with, are dealing with accountable AI can find our lessons helpful and, to help their research. So accountability, what is accountability actually? So at the beginning of the range, we are looking at maybe hundreds of papers, trying to find out what do they mean by accountability. We have a law professor actually wrote a paper about what do they mean by accountability from a legal term. And it's an overloaded term, even only in computer science. So when we talk about accountability, we talk about transparency, fairness, explainability, and other things, reviewability, so on and so forth. So, so we understand that accountability is, all the other things actually contribute to accountable AI. And so in this sense, accountability actually require some of them, transparency and fairness, so on and so forth. However, accountability has a wider range, a wider scope. So before I started the RINS project, my naive idea as a computer scientist is that, oh, what is AI accountability? So we need to hold the AI algorithm accountable by using LIME, SHARP, bias analysis, and even, some kind of performance monitoring tools, to actually record everything that AI has done, or the work out the reasoning process of the predictions. But also another view is to hold the people accountable, because people are behind those AI. However, when I talk to the law people or the social scientists or social technical people, we realize that view is not enough to fully realize accountable AI. So we have a wider range, a wider view, beyond computer science or AI. So consider AI is really complex. Has a social technical component, social legal technical, and dealing with the environment. So AI is dealing with the environment. Human is interacting with AI. Human are interacting with other humans within AI, and they have some effect on the environment. We are talking about a very complex workflows. Information flow are flowing from one end to the other end, and you need to capture them if something happens. You don't need to capture all of them, but you need to consider, these may contribute to the accountable AI. So so that is the first lesson we have learned. We need to go out to computer science and look at the other range. Even for technical perspective, AI is not about software. It's about hardware. It's about the low level, supporting functionalities and other things which help the AI. So that's something I tend to ignore at the very beginning of the RINS project. So I think the previous talk has shown this part of what is accountable AI. So this is one of the accountable AI perspective developed by our RINS team. So they have published this nice work in the conference, in top conference. And I'm not going to read this in details, but you can look at this is only one scope. It's very useful scope, and they try to help us to solve the problems. And but we need to emphasize that. But actually, if we look at the three scopes of AI accountability, so this is a nice paper published by Milan in 2018. They are talking about the three senses of AI accountability. And I think most of, I mean, at least myself as the computer scientist, I restrict myself in the first sense, that is technical science. Technical science accountability, when we talk about all the bias, the fairness, and explainability stuff, these falls into the technical part of accountability. From legal point of view, if you are looking at the laws and regulations, so the laws are not dealing with the AI, but the laws are dealing with people or the teams behind the AI. So we need to hold the persons or the teams behind the AI accountable. And another view is a complex point of view. AI is a wider range, has AI software, hardware, and lower level supporting functions and the environment, so on and so forth. And this is actually what we want to have. We want to achieve in range. We want to look at the wider context. This will affect how we are capture the information, or the way we are going to capture the information, or how we are going to look at the accountable AI from the complex point of view. All right. So after we know the three scopes of AI, we're going to answer or not answer, actually try to answer two questions. So what do we need to capture for accountable AI? So I'm going to look at the scope, the capability, the obligations, and the actual actions in order to answer this what question. Okay. So the scope means what we are going to look at, what information we are going to look at for accountable AI. Again, based on the three sense or three scopes of AI, we're going to look at the technical perspective. This is our computer scientists that we are more familiar with, right? We need to record the training data, the evaluation metrics, the robustness, performance monitoring, so on and so forth. There's a lot of automatic tools like like a model card and Google TFX, ML, automatic workflows, those kind of things. They can achieve this quite nicely. And the social human aspect, we are looking at the human decision making. Why that solution is chosen by the team, by the machine learning designer, and why a particular machine learning library is chosen by the developer, and how the human are making real-time decisions, when AI is running in the real world. And even the meetings between the human that need to be recorded, because they may be held accountable in the future. And from the complex point of view, we have the information flows across different components of AI, and we need to capture environment like a temperature, even for automatic car, and temperature, pressure, so on and so forth, because all of this could affect the accountable AI. Okay. So what to capture? So all means what we can actually capture. This will subject to the technical limitations. For example, depending on which model you are trying to use, some models are easier, to look at. Some models are harder, and depending on the hardware or other technical limitations, we consider the whole AI life cycle, and so this is easier for us to understand. And but social and human aspect, when people first designed the AI project, do we have all the information about human activity? Human may make a random choice or make a reasonable choice, but for a very old AI, we may not have those kind of information. In that case, it will be very hard to capture the information. And from the complex perspective, and the capture capability is affected by the hardware, software. Sensors, for example, the sensors only can capture a certain resolution of information, and also the legal factors. Something we can capture but we cannot, otherwise that will not following the law. And we all need to consider this before we are making the decision of for information capture. And finally is the obligations. So we talk about the laws, regulations, and the standards. Everyone knows GDPR, or most of us knows GDPR. We need to capture, what is GDPR required. And the RINS team is talking to BSI, and the BSI has published a standard for automated cars. And for example, they require, if something happened to the car, you need to capture a time window of this time window for higher resolution information. This is actually not feasible all the time. We have made our comments to BSI saying, we have some concerns about it, but this is the obligations. No matter, they are hard or not. This is something we need to think about. So once we know the first three parts, we know, what we can capture, the scopes and the obligations. What we can do is we start from the obligations. We need to follow the law and standards, and then we have a set of information we need to capture, and then we will look at the what we can capture actually. Maybe something required by the standard, but we cannot because the limitations of the hardware or software. And in this case, we can work out a narrow set of the information we can capture. And then we propose the 3 principles after we have the narrow list. The performance principle means, when you capture information, you should not affect the performance of the AI. You not make it a less reliable, for example. And the second principle is the friendly principle. You should be less invasive to AI and the environment. And the third principle is a redundancy principle. Only when we are following the first 2 principles, and the third principle, we can capture more, is always better than capture less, just in case. We also need to consider the nature of the problem and the specific accountability requirements. For example, for automatic cars, sensor information, car engine, environmental data is something we need to consider. We can not only consider the AI as itself. And for recruitment, for AI, enabled recruitment, we may need to look at the bias and the transparency, so on and so forth. So we also need to look at the problem. So we just trying to give some views, our views and lessons we have learned. So the second question is, how are we going to capture? So we should consider the entire AI lifetime. So from the very beginning and to the very end. And in each stage, it requires individual information capture methods. For example, in the design stage, the RAINS team has been working on paper for the design stage and the implementation stage, how we can do this in these two stages. But it's more important in the running time. When AI is running in the wild, how are we going to monitor them? And also for maintenance, if AI is going wrong, we need to take it offline and repair it, reconfigure it, and put it back. So in that case, how are we going to capture all the information? And also the degree of automation, this is also very confusing to me. So many people think you can just automatically capture all those information. You have got a very nice Google TFX framework. You got hardware to automatically capture the information. However, we need to bear in mind that not all the information can capture automatically. You could use a semi-automatic way, like a model card toolkit. I think the next talk will tell you more about what a model card toolkit is. It's basically involve human to input the model card, the model information, AI model information, but it can also automatically capture something else. And manual capture, sometimes we have to do manual capture, for example, to gathering the meeting record and looking at the contract, so on and so forth. I will not tell you more about what we have developed in the RAINS in terms of information capture. I just give you some rough ideas. So the RAINS team has developed a RAINS ontology. This is our core RAINS components to manage all the accountability issues. So this RAINS ontology has been connected with the model card toolkit. This will enable the RAINS to take what we have captured in the model card toolkit. And the ADD development.
Just to let you know, that's the 15-minute mark now.
Okay. Okay. This is my last slide actually. So yeah. So the ADD development and also the Cambridge people, they are working on decision provenance. They are captured the human decisions, and the Cambridge team also trying to capture the lower level information, because this is also overlooked by many accountable AI, because sometimes it may be the lower level faults cause the whole AI issues. So just let you know, we have a variety of tools to enable information capture. And so this is the conclusion, and we hope this, this is not a technical paper, but we want to just share of our lessons we have learned. And bear in mind, we should really looking at something beyond computer science, look at other fields, and including the law and the social science. And so that is all for me. Thank you very much. And questions, please, and any comments.
Thank you very much for that lovely, lovely talk, Wei Pang. Do we have any questions from the audience? If you have a question, feel free to use the raise hand functionality of Zoom. While we're waiting on people to kind of think up their own questions, I'll maybe start with one of my own. So what really fascinates me about this work in particular, Wei Pang, is bringing in the human element of accountability, because I think you're right, that's something as computer scientists we have a tendency to forget. That at the end of the day, we have so many stakeholders involved in this process. I wonder if you could maybe tell us from your experience, what sort of things constitute evidence from your various stakeholders, and how easy is it to gather from people who may not be that technical?
Yeah, I think you see, first, AI development start from user requirement, and we need to know the user requirement. So this is something user need to tell us what they want to achieve, and then there's the understanding of the AI development team and AI project managers, and this is to me, this is the beginning of the misunderstanding or confusion may happen. And so we need to look at the contract, from the software point of view. In software delivery, they have, before they are going to develop software, they need to form a sort of contract list. So we need to look at the contract list. What do you mean by this function, and what we are going to do? So this is a list of the contracts. So in AI, I don't think a lot of people are doing this because AI, itself is already really complex. So so from the very beginning, when humans have the meetings, have the decisions and the outcomes of the decision, this is some of the information we need to capture. Also, when humans are making are interacting with the AI, when they think AI is going wrong, they are trying to manipulate the AI, and this information need to be captured because their human intervention may not be the right thing. And also for maintenance, for people who are maintaining the AI, they are making the choice. For example, they are going to lower, the network traffic, and this is an important decision to many AI, and this also need to be recorded. And sometimes I would think in most of the cases, it's not the AI who caused the problem; it's actually the human who caused the problems. So because AI cannot talk, but human, can say it's not my fault. So in this sense, but at the end of the day, for the legal point of view, the human need to, the legal framework will also always target the human, not the AI itself. So, yeah. So I'm afraid I don't have a universal answer because it's everywhere, but it depending on how we are going to look at, how we can start from somewhere, we can capture some information to start with, and yes.
Yeah, I think that's one of the things that really interests me so much about this project is it's very tied to this idea of experience, like we've talked about before, because all of these experiences can contribute to that evidence base. And I think that's a fascinating idea. Regardless, I'm afraid we're out of time, but thank you very much for a wonderful talk, Wei Pang.
Okay.
And your fantastic paper. And I'm afraid it's time for us to move on to our third.
Thank you very much. Thank you.
All right. So our third paper coming up is Challenges and Future Directions for Accountable Machine Learning by Agne, Zainyte and Wei-Pang. I've probably murdered pronunciation of that. Sorry, Agne.
No, it was fine. It was fine. Try to share my screen just now.
Okay.
Okay, can you see my screen fine?
Yeah, all good. All good.
Wonderful. So hello, everybody. My name is Agne Zainyte, and I will be presenting my and Dr. Wei-Pang short paper on challenges and future directions for accountable machine learning. So machine learning is a type of artificial intelligence that is capable of learning from data and improving itself accordingly. And that's what makes those systems so special when it comes to understanding the rules that govern the automated decision process. Due to relatively recent increase in computational power and growth in data sets available, such machine learning systems became applied in several areas such as healthcare, finances, banking, marketing, etc. And as anticipated, it has brought the attention of EU's General Data Protection Regulation, or better known as GDPR Commission, which has now established a legal right to explanations of decisions made by automated means, such as those by machine learning algorithms. And therefore, the urge for increasing regulations and rapid expansion of machine learning applications and situations that if an error would occur, it would result in detrimental effects of human lives, think disease diagnosis or mortgage applications, all this further accelerate the need for accountability in machine learning systems. So let's start with establishing what do we mean when we say accountability in machine learning. It's almost possible that each of us could describe what do we think accountability means, and we would probably get a wide range of answers. So for this presentation, I will be using Cambridge Dictionary definition of accountability, which is the fact of being responsible for what you do and being able to give a satisfactory reason for it, or the degree to which this happens. But once we have a solid definition of what accountability is, we need to ask ourselves, how can this be applied to self-improving systems where we as developers are not the only decision makers? The system learns from data and it proves itself. So let's start by looking at currently existing frameworks for accountable machine learning. The first one is Model Card Toolkit, which is a Python library developed by Google. The library assists in generating model cards, which is a documentation that holds information about model that was developed. The goal of model cards is to prevent mistakes caused by systematic failures that become apparent only system has been put to use. Model card does so by storing information about ethics, provenance, usage, and evaluation of the model. Model Card Toolkit library contains a collection of tools that assist developer in compiling and filling in model cards. And therefore, the greatest advantage, what makes this framework so great, is a semi-automated process when creating documentation, because it's efficient and easy to use, and you don't have to spend so much time on it. If you worked on a code already, you don't want to spend that much more time on accountability. However, it has this limitation that model cards are generated only after the model has been developed. So imagine a situation where you start developing a model, you don't finish it, you put it in a Git repository, it's open source, developer number 2 gets your code, works on it, it doesn't have model card, it doesn't have that information captured in there. And to give a better understanding how model card looks like, here's an example of model card for breast cancer Wisconsin dataset. So there are some details that have been captured by the developer. There's some capture from the code, some visualization tools. So as I mentioned, it is semi-automatic. Some of it is being captured from the code. Some of it has to be filled in by the developer. Another framework I would like to bring to attention is datasheets for datasets, which was proposed by Microsoft research team. Rather than being a library, it is a framework for documentation that would be attached to the datasets that are used in the model. The goal of datasheets is to have a standardized way to document how and why datasets were created, what information it contains, and which scenarios it is applicable, and whether it might raise any ethical or legal concerns. Each datasheet contains a set of proposed questions that can be segregated into categories, such as motivation, data pre-processing, data distribution, data maintenance, legal issues, and ethical considerations. The greatest advantage of this framework, and why it is included in this presentation, is because it acknowledges that datasets could and should be held accountable as they dictate how machine learning system will learn about the so-called world and what rules it would infer about it, because data plays a big part in it. However, as it will be demonstrated in a slide to come, the framework only aims at written qualitative information, which is solely depending on developer to be filled in. So here is an example, overleaf example of datasheet template. And as you can see, it simply proposed questions requiring some answers. I suppose it could be good that it doesn't require any coding because anyone can understand it, but at the same time, it's quite hard to capture it in model cards in any automated way. The first framework that is growing in popularity is fact sheets that was developed by IBM research team. It was inspired and built upon model cards and data sheets, and therefore it could be seen as an extension for either. The goal of fact sheets is to prevent overgeneralization of models, which would in turn help to reduce the errors that are a result of unintended use of these models, which is very similar goal to that of model card. Each fact sheet contains information about relevant attributes of machine learning models, such as intended use, performance, safety, security. It also encourages additional information to be provided, such as how model was trained and deployed, some use case scenarios, legal considerations, as well as ethical considerations. The framework is still in ongoing improvement, and I believe it is the greatest advantage of this framework that is in active development. We're working closely with potential users of the framework. So the research showed that the framework involved user-centered studies, which are then turned into improvements, incremental improvements, and therefore develop machine learning scientists and data scientists can decide and propose what information should be captured in data sheets, what is the most useful, what works, what doesn't work. And however, the greatest limitation of framework is similar to that of limitation in data sheets, that the information required to be filled in is quite excessive, and it has to be filled in by the developer because as of right now, there's no automated means to do so. And here's an example of a fact sheet. And given that we've seen how model cards and data sheets looks like, it does look like a hybrid of both. It seems to capture information of both. So it has about training data, but I think what is the strong point of it and improvement is it also talks about robustness, which is, I think, important part of accountable AI, as well as about explanation, as explainability is also important part of accountable AI, but nonetheless, it is not perfect yet. So let's move on and talk about challenges in accountable machine learning frameworks. In current frameworks, accountability and transparency are almost used interchangeably, but it should not be forgotten that while transparency is an important part in accountability, it's not the full picture. Therefore, there is a challenge to distinguish between those two, where transparency of the algorithm stops and accountability starts. The second challenge would be is the fact that majority information is being captured manually by the developers, and if there would be a more efficient way to do so, there's another challenge to capture information more efficiently that wouldn't be so labor intensive. And the third challenge is to be able to capture the behavior of the model and to show how model works as a whole. Because as I mentioned, the model, there's not only developers who are involved in automated decision-making, the model itself learns from the data, infers the rules, and based on them makes a decision. Therefore, it's important to understand how the model works. Next, let's talk about what recommendations can be made for the future frameworks. For example, causality. Current frameworks have no stage-to-stage analysis, which means there is no information about causality that each stage of machine learning development has on the other stage, or each component developed has towards the final decision of the product. And by understanding the effects that each machine learning system component has, the design of the machine learning system could be improved by making sure that effects and causes are clearly understood. It will also assist in the traceability of automated decision-making, because causality identification could compensate for the opaqueness found in algorithms. It would also compensate for lack of transparency in algorithms where full transparency or detailed transparency is not wanted, given that model is not open source, or perhaps it's developed by a company that is on a competitive edge and doesn't want to share their product with their competitors. And this way, causality would assist in implementing accountability by enhancing partial but important information about transparency and explainability. So it wouldn't be about the quantity of information, but about the quality of information. Second recommendation for the future frameworks is decision provenance. It would involve methods providing information about decision pipelines and would show how data flows throughout the model and what connections were being made. So this is much closer to explainability, part of accountability. Transparency and decision provenance could also allow developers to be proactive during the model development process, assuming that each component could be tested individually before full deployment, which I will talk about in the next slides. And it would allow to mitigate the risks associated with automated decision learning. Decision provenance could work symbiotically with causality capture. It would further enrich the understanding of how algorithms form decisions and what component of the system's powers they change at some point, which would give a great insight about models' behavior, which is information important for accountability. And the final recommendation is computational tests. It is a powerful preventative measure that would be implemented in the form of tests that would check whether a machine learning system behaves the way it is expected to behave. Such tests would register the errors that occurred if model have failed the tests, would show what is capable of doing and not capable of doing. Additionally, tests could be applied to so-called hidden information of the model that is not possible to visualize, for example, to high dimensionality, and also is quite hard to understand from the code. So therefore, by testing the behavior, we could analyze how the model works. The main motivation for such computational tests would be that it would allow to understand how model functions and whether it works. And it would work instead of the big red button that would just allow you to stop the model once it went rogue. So this way, the component would be working fully and the model wouldn't behave in unexpected ways, because ideally in accountable machine learning, things would never go rogue, or at least not without an explanation at where the error occurred. And therefore, in conclusion, there is a high demand for effective and efficient framework for accountable machine learning. Although there are several frameworks already put in use, these are mostly focusing on transparency and information that is known by developer However, our recommendations for future frameworks is an additional information about how model works as a whole. And this could be done by implementing causality, decision provenance, and computational tests. Here's a list of references that have been used in these slides. And with that note, I will end my presentation here. All questions are welcome.
All right, thank you very much, Agne. Do we have any questions about this very interesting talk? If people are still thinking up and preparing to put up their hands, because I know it's a scary prospect on Zoom, then perhaps I would get us started. So I really like the different frameworks that you've demonstrated, and I think I agree that these look like really interesting avenues of recommendation that you've highlighted, Agne. I wonder, where do you think the user fits in this accountability? Because a lot of our previous talks have talked about stakeholders and that human element, and I understand that's something that's difficult to capture at a framework level, but I am interested to get your opinion on where you sort of think that information fits in among these frameworks that you've talked about, or indeed recommend.
I think this automated capturing of what model does should be additional to others. On its own, it's not enough. But what I noticed in looking at already existing frameworks, that they all, so when it comes to machine learning, it is a black box, and that's where there's explainability. We don't know everything about it. We don't know how it reaches its decision. And as a very definition of accountability, there must be an explanation for it. And therefore, we must understand the behavior of the model. And the user could still be there. And there's, as has been mentioned before, there were great insights that accountability, it's more than just a code. It's a lot. It's norms, it's regulations, it's beliefs, what is right, what is wrong. It's a really wide topic. But I think what is lacking in current frameworks is this exactly capturing of what model does, because model also is involved in automated decision making, and sometimes as a humans, perhaps we just can't capture that information. We don't know it, because in the current framework is a developer who provides the information, and I believe there might be some information that can be only accessed through those computational tests.
Okay. Thank you very much, Agne. I see we've got two hands raised. The first was from Fatima Ganduri.
Hi, I'm just wondering, do you think accountability can be reached by applying interpretability, and kind of the idea of interpretability based on use case? For example, let's say I want a certain accountability for a certain, let's say, use case. Can I have multiple scenarios that help interpret a model, and would that create accountability, do you think? Love to hear more about it.
Yeah, I think it would definitely would, because yes, because for the way I understand accountability means if the decision was made, you need to, and you have to have a satisfactory explanation, and therefore the model has to be interpretable, explainable. So yeah, I think it would definitely, it does fit in accountability. I think so. One of the points I was trying to make, that accountability is not only transparency of the model, there's so much more to it.
Awesome, thank you.
All right, thank you very much. And perhaps a final super quick question from Ike.
Yeah, thanks for the presentation. I think from what you described regarding the fact sheets, and so it shows that it's still very subjective on what it's used to represent the accountability of the models. You also mentioned the need to maintain some opaqueness in some situations. So I was wondering, could a system be really accountable if it's not fully transparent?
So thank you for your question. This is something that I read in one of the papers where they were discussing whether full transparency is really needed. And I kind of agree on that as well, that it's not the quantity of information, but it's the quality of information that is important in accountability. I think this is where I stand. So I think there could be cases when you don't want full transparency, when you want model to remain opaque to other users than those of developers. And in that case, if there is information who's being captured and the model can still be held accountable without being fully transparent, it would be great, because I could think it would make the whole implementing of accountable machine learning much more attractive, because it means you don't have to make your code open source to everyone, kind of. Yeah.
All right. Thank you.
All right, thank you very much for the presentation, Agne. I'm afraid that's all the time we have for questions. I'm sure there will be time later in the breakout rooms if you guys want to talk more about it. But for now, let's move on to the final paper in this session 2, examining roles within an XAI system, and that is the human-in-the-loop approach to digitization of engineering drawings by Andrew M. Fagan, Graeme M. West, and Stephen D. J. McArthur, as I bite my tongue at the end there. Andrew, I believe you're going to present?
Yeah, just getting the slides up here. Yep. That coming through okay?
Absolutely perfect, Andrew. The floor is yours.
Okay, right. So yeah, I'm Andrew. I'm the, this is my PhD work, sort of an early stage summary of it. I'm just going to talk through it and why it's sort of an interesting problem, I think. If PowerPoint will work. There we go. So engineering drawings, as many people will be aware, are sort of an important part of engineering. They're used both to design new systems, and also after a system's been constructed, they're used for redesigns, maintenance, asset management, and really they're just absolutely crucial at many stages of industrial processes. So if you've got some really well digitized engineering drawings, you can span through an entire power plant or an entire whatever other industrial system that you care to name. You can span through it really quickly. You can identify which components connect to others. You can identify which entire drawings affect others. But unfortunately, in many of these industries, stuff was designed decades ago on paper. The assets are still in use, and they've never actually been digitized. Now, the process of digitization takes several hours for a skilled engineer to perform. So what ends up happening is you've got scans of the drawings that the engineers, instead of spending all the time to redigitize them, they just perform the slightly slower process of using the scanned documents every time. So you can see straight away intuitively, there's a chance for a boost in performance, a boost in efficiency and intelligence here. It's just we need to actually spend the time to perform this task. So my goal of my PhD research is to augment this digitization process. So digitizing engineering drawings has been a thing that's been of interest basically since about 10 minutes after the drawings were designed. Someone went, oh goodness, these should really be on a computer. Unfortunately, it's proved to be a really hard problem to solve, as you might imagine. Early approaches in the 80s used all sorts of image processing techniques. More recent techniques, including some work by Marina Garcia, has used all sorts of really interesting types of classifiers, have used generative adversarial networks to solve problems. But it's still by no means a solved problem. There's still active work being done here. So I mention this here because it's going to come up later. Marina Garcia identified 3 key problems, or key challenges to asset digitization: quality, skewing, and topology. So I'm going to be very brief to repeat those. And I believe Dr. Marina Garcia is actually in this chat. So if I get this horribly wrong, feel free to jump in and tell me. The quality problem refers to the fact that the images we're digitizing are fairly low quality, fairly badly scanned or poorly formed because they were handwritten, which it creates sort of obvious problems. The skewing problem refers to the fact that some symbols are dramatically more common than others. So you can see a sample from a data set on the right here. Just straight away, some symbols appear all the time, some only appear once, and that obviously creates a class imbalance when you're trying to create a classifier, where, you know, if I output something that always says whatever image it identifies as a relay or some other symbol, then maybe it gets like 90% accuracy, and that's obviously not very useful. And then the topology problem is, even if you identify all the symbols and the text in a drawing, sort of putting it back together, figuring out how they all connect to each other isn't trivial. So, as I said, some people have managed to create really good classifiers using sort of rich existing data sets. In particular, there's a class of drawing called P&ID diagrams, piping and instrumentation diagrams, that a lot of work's been done on specifically. So that class of drawings now has a nice data set that people can work off of, which serves as obviously a basis for trying all sorts of interesting AI techniques. That's unfortunate, or that's sort of one of the key places where this nuclear application is different, because we don't have access to that that rich library of data. So therefore, part of the challenge here is figuring out how to bridge the gap between having no data and being able to use these interesting solutions that already exist. Another example here, Turkle et al. Managed to create a converter that scans in engineering drawings from books. So these were originally produced by computer, now only exist on paper, and have been scanned back in and digitized. And their system works really well, but it doesn't address the quality problem at all, because these are drawings that were created by a computer in the first place, and therefore they're very, very well formatted, very consistent, which also isn't the case for the drawings we're looking at here. The other thing is that the number of researchers tackling this is quite small. So in a lot of papers, you'll see someone say, this is in principle solvable, this can be done, but just not enough people are working on it. So one other thing before we get to some work that's actually been done, instead of me just repeating the achievements of others, why human in the loop? So in the nuclear industry particularly, at least according to my industrial partners, no matter what you do, there's pretty much always going to be a human involved in an AI that you've built, just because there's a lack of trust. Even if you've got a really transparent system that's very consistent, they're going to want someone skilled to just check that it's right, because obviously the stakes are very high. So no matter what we do, we've always got this performance bottleneck that a human is there and has to perform some action themselves. So the idea here is, if we're stuck with that anyway, let's see how we can leverage it, and let's see how we can improve performance using this person, instead of just having them be a passive participant that ticks off the work at the end. So with that in mind, I've designed this sort of high-level framework for digitizing engineering drawings. So you see here, a bank of AI modules gets a first pass at trying to label the drawing. You can see they've, in this hypothetical example, they've labeled some symbols, they've drawn a line between them. That then gets turned over to a human who gets a nice user interface that they can add things that the AI missed, delete things, create new connections. And what we do is we log everything that they do so that we can learn from that further in the future. Another crucial thing is here, the human has just solved the problem for us. So that is now the output of the system. A lot of systems that try and involve a human like this will then start performing a sort of back and forth where the human keeps having to relabel things until the AI gets it right, because the focus is more on it being the way the AI learns, whereas this was proposed to be the actual holistic system, the final deployed version. And then that data is all logged, and we've got a bank of what I've called data presenters here, which are just things that turn that big log of data into sensible data sets. For example, that turn everywhere that a user has labeled a coordinate as being such and such a symbol. It creates a database of images of those symbols so that you can create a simple classifier for it, for example. So the hope would be that if you do this, initially the AI is absolutely rubbish. So the human is doing all the work. So the user interface actually should provide almost a speed up compared to just manually digitizing the drawings. But over time, the user gets a more and more complete starting picture when they begin. So their active check is still here, and that sort of satisfies the auditability requirements, but they remain an active participant. But as the AI gets better and better, the speed of this whole process should improve and the human's workload decreases. I've probably gone through that very fast because I always speak ridiculously quickly and these sort of things. So we've got to conclusions already. That's no problem. So the framework, I would contend that it addresses the quality and skewing problems, because it means that even if the AI make these common mistakes, that doesn't reach the output of the system. The user has an opportunity to finagle that, and it doesn't end up being, an incorrect output, because the human's still involved and we still learn from that. It allows many techniques to be explored in parallel. So as I've said, there's a lot of really good work done on this already if you've got some data, and we just don't have the data. So as we do this over and over, we build up a larger and larger collection of data. Some of our techniques become better, some techniques become unlocked to us, and probably some become less useful, because once we've got the data, other techniques are more useful. But that's why we've got the modular bank of AIs that we can just throw them all at the problem. This also means that we don't have to worry so much about figuring out exactly what the right algorithm or what the right method is. If we instead focus on a wide array of sort of out of the box solutions with minor adjustments, we hopefully get a higher level of performance without having to reinvent the wheel. Future work, we aim to apply the framework to other problem areas. We've had a bit of discussion. It's been identified that there are other problems that actually end up being quite similar to this digitization problem. For example, I say here scheduling. If you've got a system and you've got a bunch of tasks and some need to follow others and some can be parallelized, right now that's a human has to go through and work that out. And sometimes if you get an AI to do it, it'll create something that sort of solves the problem, but it misses obvious real world things. So again, they always want a human there checking it. So you can apply a similar technique to this for problems like that. Again, I'm aware I've talked through that very, very quickly, so I'll open up to questions, and if I've blazed past anything and anyone's sitting there baffled, please do feel free to ask, and I'm happy to repeat anything.
All right, thank you very, very much, Andrew. It didn't take long. We already have a question from Dr. Marino Garcia himself. So, Carlos, if you would like to ask your question.
Sure, Cal, thanks. Hi, Andrew, nice to meet you. Please call me Carlos. And yeah, nice to see that, the work that we've done over here has been seen over there. Indeed, we have been working with the oil and gas industry for quite a while in this same problem. You should be aware of that. And you got everything right. I mean, the challenges and the techniques. So congratulations on that. I don't have anything to object about that. My question is regarding to the human in the loop interaction that you mentioned, which is obviously the way to go. I agree with you. And the thing is that, as you claim, if you, for example, correct a symbol, right? So if you change a label of the symbol, there should be an improvement on the performance of your AI, no? But if you correct two symbols, then I guess that this, let's say, improvement should be exponential, no? Or at least, there should be more benefit of doing two corrections rather than one. So my first question is if you have any idea of how likely is that this is exponential, or if it's not that exponential. And the second one is regarding the connectivity of the diagram. So as you may know, also, it's not only about detecting symbols, but also about detecting connecting lines, right? That connect one symbol to the other and giving the engineers the information of the topology. of the drawing. And do you think that human in the loop can also be used to correct connections that were missed and things like that?
Yeah, so I'll I would start with that part of the question, because yeah, I think I've given that part quite a lot of thought. Originally, this diagram was basically twice as long, and it had a symbol and text identification block. And then once that was completed, went over to a completely separate topology block. But what I eventually sort of decided on was that the higher level simplicity here was probably more valuable, because you can still have some order within like the AI modules, where, for example, you let it identify all the symbols, and then on those identified symbols you run your best sort of topology reconstructor. I also think whether it helps to solve the topology problem, I don't think I'll know until I can test it. But one thing it does do is minimize the impact of the topology problem, because even if the AI is absolutely terrible and doesn't find any correct connections, the human's still on hand to make those connections, and that's still the human's job being easier, because one step has been done for them and they're just joining the dots. Sorry, I've talked so much there that I forgot the first half of the question.
No, well, it was just that the fact that if you had any thoughts or ideas on how, let's say, how much interaction does a human need in order to, let's say, get better performances? I
think early on, the more corrections you make will, as you say, probably have a really exponential increase in performance. For example, one of the techniques I've experimented with is a thing called QATM. It's a form of template matching that only takes one data point of each class that it's identifying. So that's obviously a very simplistic example, but if you ran this once at the point that you've identified one of every symbol, suddenly QATM becomes possibly really good. And then as it goes up and up, QATM probably drops off compared to if you've got thousands and thousands of examples. CNN's probably the way to go, but just can't get there yet. I think probably individual corrections are never going to make they're probably never going to change the whole system, especially once you've got high amounts of data. But I think doing this over time should, theoretically, it should never get worse, I guess, is the hope. So you're always going uphill.
Yeah, that's the interesting part. As long as it doesn't get worse, I think that's very important. But I think that could be a potential good paper in this area, because a lot of people just publish, like we did this, like they just present the final outcome, but presenting some sort of assessment of different techniques for human in the loop and how they improve the accuracy or the efficiency of the system. I think that would be a very interesting type of publication in this area. So yeah, happy to keep discussing this. I guess that we could be speaking about this forever, but we have other sessions and things to speak. But yeah, nice to meet you, Andrew, and very nice work.
You too. Thank you.
All right, I think we have time for one more quick question, and I see we've got one more hand. So Sadiq, would you like to ask your question?
Thanks, Kyle, and thanks, Andrew. My question is, when do you decide when to retrain the model or the models?
That's an excellent question, and it's one that I would probably leave up to. Really, it's on the individual models. If you're designing, if you know yourself as you're building an AI that goes in this sort of bucket of AIs, that every single piece of data will make a huge impact, then I would suggest that that's probably the best thing to do. Whereas if you're talking about a CNN, you could probably leave it, a few days at a time, because as I said to Carlos there, one piece of data probably wouldn't make that substantial difference. But the answer is it would probably be up to the individual modules to decide when enough new data has been gained to make it worthwhile.
Sure, thanks.
Thanks.
All right. Thank you very much, Andrew. I'm afraid we're hitting time. So that's all the time for questions we have at the minute. Like I say, there will be this breakout room activity later where hopefully you'll get an opportunity maybe to speak to Carlos and Sadiq in a bit more depth. But that is it for session 2. May I say a huge thank you to all of our presenting authors. You all did very, very well, and it was absolutely brilliant to see your presentations. We are now going to stop for lunch. We're a little bit behind schedule, but we're going to try and stick to the 40-minute lunch period, or at least the idea thereof. So we will be back and we will be starting session 3 at about 2:15 in this afternoon. Until then, once again, thank you all, and I look forward to seeing the rest of the presentations this afternoon.